Hello and welcome back. I hope you enjoyed your virtual booth crawl, and now we're back with Trevor Norris. So Trevor works at NodeSource during research and development on different metrics and insights that can be gained from the event loop and how to utilize it to improve monitoring and scaling that use Worker threads. He's been a Node.js developer for over 8 years, and 5 of those he's been a member of the Node Technical Steering Committee. So please welcome Trevor Norris with the introduction to Event Loop Utilization.
So, thank you everyone for being here. Glad I can be able to give this talk about all the research I've been doing over the last year pertaining to event loop utilization and about event loops in general. So to start off, we're going to talk about Node's event loop. This diagram you see is the event loop that appears on the Node.js official documentation. It has all the different phases that you see. But the problem is that this event loop isn't simplified enough. It isn't close enough to the conceptual event loop. There are a lot of implementation details to be concerned about that make things too complicated when you're trying to reason about how the event loop works. So to simplify it, we can look at the event loop as having only 2 phases. The first one is the event provider, and the second one is the event dispatcher. And there's just a couple simple operations it goes through. So first, events are received from the event queue, such as the kernel, through the event provider, like epoll wait. Now, if an event is waiting on the event queue, when the provider is called, it is immediately returned. If no event is waiting, then the event provider will block or idle until an event arrives. Now, when the events arrive, they are dispatched. Now, this is different than calling the callback. The event handler is the calling of the callback. But since libuv can do more than just calling the callback, such as stop listening to the file descriptor, that step is called the dispatcher. Now we're going to go on to a timeline of an example execution of a few event loops. So the top line is the event handler. The second line is the event queue. Now in loop 1, the event provider is called. No event is waiting in the event queue, so it idles. Once event 1 arrives, it's immediately passed back up and processed, while that duration of time before event 1 arrived is what we'll call idle time. Now, while event 1 is being processed, events 2 and 3 arrive. Then, once event 1 is done processing, loop 2 starts. Events 2 and 3 are immediately returned and processed, and likewise, when they are being processed, event 4 is placed on the event queue and then returned and processed. One thing you should take notice of in this diagram is that the event loop starts at the poll phase, unlike with Node's event loop here, where poll sits in the middle. Because of implementation details, such as needing to run timers and possibly skipping over poll to do certain things, the proper conceptual event loop runs poll first. So why does this matter? Because it's easier to reason about what happened in a loop once it's simplified. And when I was doing my research, I first started by adding metrics, counters, and timers to every facet of the event loop I could, every phase of the event loop. And in the end, I was tracking about 30 metrics, and very quickly it became apparent that I wouldn't be able to make sense of all the data. It was impossible to make correlations with all of that data because there was just too much of it. So over time, I stripped down and eventually came down to a very small subset of metrics. And I realized that using that small subset of metrics, I was able to get information about the event loop without losing any accuracy. And by doing that, I was able to extrapolate using the simpler information into more of what could be used for metrics and monitoring. Now, this works because we can think of all work being done in the event loop as work that needs to be done because an event fired. Yes, you have timers and it can do miscellaneous. It's just helpful to think of timers and think of all work as work done as an extension of an event. So first, the idle time. It's the most basic event loop metric, and calculating idle time conceptually is simple. You just say it's the amount of time blocked or idle within the event provider. Unfortunately, it's not that easy to calculate. We'll get to that in a little bit. Actually, right now. So one of the idle time implementation notes is that now the event provider APIs such as poll, KQ, and all the others, they don't have any option of returning if there were any events waiting in the event queue when it was called. So in order to accommodate calculating idle time correctly, I patched libuv to first make all the first times it calls the event provider, it always does so with a timeout of 0. Once it does that, it will immediately return whether an event is available or not. If an event arrived, when it immediately returns, the event is processed and execution continues normally. If there are no events, it will call the event provider a second time immediately after, except that time, it will measure that call into the event provider as idle time. Unfortunately, any performance overhead of needing to make calls disappears once the load increases, because then events will usually be waiting. So it's not something you need to worry about having any performance overhead. Now, onto what is event loop utilization. Well, simply defined, it is the percentage of time the event loop is not idle. And unlike CPU, the event loop utilization, or ELU, can never be greater than 100%. And the ELU can be used to our advantage in two ways specifically. First off, we'll find, as we'll see, it's a more precise way of measuring the process's capacity, and the ELU can be used to get information from each worker thread. There is not a cross-platform compatible way of retrieving thread-based CPU usage, but ELU can be calculated for every event loop running on every thread, helping us monitor all the workers. Now, event loop utilization has landed in both perfhooks and worker threads, and we'll get into those in the example usage. Now, first, we're going to look at some graphs of CPU versus ELU to get better understanding what's going on. We'll just jump right into the graphs. And on the left here, you'll see request per period. On the right, you'll see the percentage of ELU and CPU. And on the bottom is the number of connections as they increase. So these two graphs are simple example servers using, as you can see, most of the amount of time spent in the process is spent in the main thread running on the script. These are the two simplest examples of how it works, where they trend closely. Now, as you'll also see, the servers have different scaling curves. One tapers off gradually, the other one is very linear until it hits full capacity. We'll get into that a little bit later on. Now here on the right, we have one that's generating a lot of garbage, it's generating a lot of objects requiring the garbage collector off the main thread to collect that. As we can see here, that the CPU can be substantially higher than the ELU. But the bottom, likewise, it's where the crypto library is doing off-thread work, and it has about the same look and results as the garbage collector. Now here we have a worker thread example where we can see in the top left, we're using worker threads to process requests by doing templates. And while the requests do taper out, we'll see that the ELU doesn't. In the bottom right of that first graph, we'll see it's about 70%. And we can use that with you as a way to calculate the number of worker resources that need to be dedicated in order for that process to reach maximum capacity. So it was done again using that estimate in the bottom right. And as you can see, the number of requests increased about by 100 per period. Now, real quick, the request per period is different than request per second. The request per period is the number of requests that can be done within the collection period. It's a correction mechanism that I found gives you better statistical data when doing cross-process comparison of what's happening. Here are two interesting examples. The first one is the same worker thread script, except that it's running within a container, and I only allowed it to use one CPU worth of resources. But as we can see, it hits the CPU max very quickly, and so does the request per period. But then the ELU is very slowly, but almost indistinguishably ramping up. And that's because what's happening is just kernel swapping other stuff. But we can use, if we look at our total CPU usage along with ELU, we'll be able to notice that the limiting factor here is in fact the hardware and not the software. So CPU, while in terms of monitoring isn't as useful as ELU, it is still useful to use in correlation with each other to find other situations like this. Likewise, at the bottom, in this scenario, the file system is writing synchronously to a network drive, and as you can see, CPU is actually substantially lower than the ELU, meaning a lot of time is blocked and a lot of time is idle, but since it blocks the event loop from proceeding to process other events, it is considered not idle time. So we're going to get into a few example usage scenarios. This first one is a simple case of just using the three basic forms of the API. First one is you're getting the amount of the ELU from the beginning of the thread, also from between 2 points in time. That's very similar to HR time. And then the last one is just a little addition so that you don't have to do the math on your own of just subtracting the 2 times to get the difference between 2 points in time. And here's a very simple example of using it to record the ELU in an external collector of some sort. Basically, you need to get first time and then you update it. It's very similar to getting CPU usage in this case. So here is an example of how to use ELU as like a first check to see if how your process is doing within the HTTP server. What we care most about when we're serving requests is our ability to serve them quickly. And if idle time ever increases, then we know that the event loop has had a chance to breathe, that whatever request that is being received did not have to wait in the event queue. And so what we're doing is we're measuring the ELU in each request, and we're taking the difference between the 2 times. Now, if you look down at the if statement, you'll see that if idle is equal to 0, meaning the event loop might have been able to turn and iterate, but it didn't ever have a chance to idle, meaning it didn't have any chance to breathe, and events were always waiting in the event queue to be processed at some point. And then the active time is the amount of time, the active time is the amount of time it has been running in total. So if active time is over the threshold and it hasn't been idle, you can use this as a first step to make sure that your server is running okay. If this never fires, then you honestly don't need to worry about anything else. Even if CPU gets pretty high, as long as the event loop has time to breathe, that means it has time to process requests. Now, this example demonstrates how to use a message channel between two worker threads, a worker thread and the parent thread, to send the ELU from the worker thread to the parent thread. And it's a total mess. So to get around that, I added this API recently to the worker API, where you can directly retrieve the ELU of a worker thread from the worker itself. Now, this is a thread safe call and it's immediate. So you can retrieve the ELU from the worker whenever you want. And you can retrieve it whether the worker thread is busy or not. So you can monitor your worker regardless of the worker state. All right, another area we can use ELU is an anomaly detection. Since ELU is a more reliable way and a more consistent way to measure the metrics and the state of the application, it can be used to see, we can use it by comparing several different processes together at the same time. As you can see on this chart on the right, we see on the x-axis is the ELU, on the y-axis is the CPU, and there's a fairly solid trend line between most processes, but then there are two that lay outside of the norm. Now this can be used manually or automatically to connect CPU profiles or heap snapshots to let us know the differences between a normal process and an anomalous process. Now, last thing we're going to get into is an idea I have of scaling by responsiveness. ELU gives us an ability to do more with checking the state of our applications. Now that we have a better way to compare applications and processes, we can group them and trend them. So what is the idea? What's the purpose of scaling? Well, the purpose of scaling is to allow us to give users a good experience. If we wanted to save money, we would go ahead and not scale our applications and users would just have to wait for a response. We don't want that. So then why is it that we don't scale by responsiveness of the application instead of by CPU usage? CPU usage is just sort of an arbitrary value, like CPU of 80%. We're just hoping that around 80% things will get bad enough that we have to scale. But we're now able to do something better. Here are two graphs that are comparing the latency per request, and in the red is the events per loop. The x-axis again is ELU. So it's doing a comparison of multiple processes together, and as we'd expect, as the amount of work increases, the trend of the number of events and the amount of latency per request increases as well. And using this, you could create a model of when exactly you should be scaling your application. If you wanted linear, if you wanted linear latency and a solid experience, on the first graph, you could wait until 70%, but on the second graph, you could go till almost 80% before any users would notice any difference in the user's experience. Now, the advantage of this is that you have better control over the user's experience, but also you're able to more closely you're able to save on resources, because if you always arbitrarily chose a specific CPU amount, then you don't know whether you're wasting, if you're allocating too many processes and paying money in a server that you wouldn't need to. And the advantage of using ELU also in this case is that it has pretty much zero overhead. To measure the overhead, you're measuring CPU instructions. Now, this one is another example HTTP server that I ran, and as you can see, it's almost linear all the way up to 100%. And this is a good example of knowing when to scale and knowing how to scale that can save you money in terms of server costs. You can not scale until 90%, and users won't really notice a difference. And the bottom one, the sporadicness, you can see a good indication of the worker thread capacity. The overall trend line is fairly flat all the way up to 100% ELU, but response times then begin to scatter after a certain amount, because just the way that the hardware or the kernel allocates time for each worker thread and CPU dedicated resources. And this is fairly normal, but at least this way you can still get a solid trend line of how things are going. This one is especially interesting. Excuse me. This one is especially interesting because of this weird curve that it has. Now, when this happened, I didn't believe these values in this graph when I first saw it, so I spent hours redoing it, retesting it, measuring it from different angles. But in fact, this gain curve looked like for this HTTP server, where linear right up until it hits a point, and from what I gathered, V8 was having a hard time processing what was happening, so it spiked really fast. But then, as you see, CPU as the amount of usage increased, suddenly V8 could process things better, and latency per request decreased up until it reached maximum capacity. So the takeaway from this is that by improving our understanding of the event loop, as we have done, and implementation in the ELU, we're able to make more consistent metric. We're able to take those metrics and make more consistent cross-platform comparison or cross-process comparisons, use that data to be able to help us create the trend lines and understand our application better so that we can scale more intelligently. And the other thing is that, as we saw, for example, in this case, that when you're doing load balancing of your servers, you should absolutely measure the scale um, of the entire breadth of utilization, because you might run into these anomalous things, and you can measure those and know those, and then go back and reevaluate if you need to change something or determine exactly when you should be scaling. Because during your load testing, you could create an example trend of how you believe that the process should run, and comparisons of that along with what the processes are actually showing as they do, to see if your model of how you think your application is going to run actually works. I think that's about it for my presentation. Thank you very much.
Okay, thank you very much, Trevor. That was incredible. The idea of having I've worked in projects where our main scalability metric for increasing the number of boxes we have going is the CPU. So something which is a much more, what you're describing is a much more robust and extensible measure of it, which is it's a lot it's a lot better than CPU, which is quite a random-ish thing, I think is what you're trying to say.
Yeah.
How easy would it be to start using this in production? Is it something that's available now, or is that it time
Yeah.
to get into production?
No, well, in terms of usage, it's landed. It's now available in version 12 and up. So you can begin using retrieving event loop utilization via the Perfox API starting in version 12. And it honestly, in a way, can just be a replacement for CPU. So if your baseline is just to scale at a certain percentage, you can swap ELU out for CPU and scale that in.
So it should be relatively straightforward, provided you're
Yes, it should
using
be.
the version 12. Cool.
Yep.
I'm just going to check to see if the channel's got any questions for you. Just to remind people, you can ask questions on Slido, which is either through the Q&A tab or through the chat tab. I don't think there's anything else coming through. No, I'm not seeing any additional questions, but if anybody needed to get hold of you after thinking about this, so you are available on Twitter, aren't you?
Yeah. Yes, I am. Twitter, and then also IRC in the Node channel. If anybody wants to hop in, send me a message in some way, and I'll be happy to help you out and give you more information on how to use it or usage examples. The ones I gave today are fairly simple, since ELU can be used similarly to CPU. Like I said, you can use it. You can use it almost the exact same way that way. Also, the documentation, I made sure to include examples and a couple of pitfalls of what you may or may not expect, so you can reference those as well. The tests are really comprehensive in terms of what they measure. So if you feel so inclined, you can also look at the tests.
Oh, brilliant. Thank you ever so much, Trevor. That's really, really helpful.